Has anyone ever played Mario Kart? Come on, some honesty out there. Yeah, a good portion of us. I kind of like the part where you fly over something like that. It's kind of cool. But in designing this, or working with something maybe a little more realistic, designing airplanes, there's three different types of motions that you have to account for: pitch, roll, and yaw. And those three different motions require three different sets of axes. It's no longer enough just to have an x and a y axis. You have to have x, y, and z. So this is how they all line up. Your z-axis is going to point north, at least according to our book. If you do a Google search on x, y, and z-axis, there's absolutely zero agreement out there. When you click Google Images, it is so hard to find something that has the same orientation as our book describes things. They call it a right-handed system because if you curl your fingers around the z-axis using your right hand, then your thumb points north, your finger here points in the x direction, and then this one points in the y direction. So whatever, a right-handed system. Let's work with this a little bit and try and get familiar with these new coordinates. Like I said, it's x, y, and z. Whenever you're dealing with coordinates, they're always going to be listed in alphabetical order, at least by any self-respecting mathematician. So let's take a look at problem number 22. Problem number 22 wants us to label a box with these coordinates: 0, 0, 0, and where's that one? 4, 2, and 2. You know what? Let's just change that a little bit, just to make it a little bit more interesting. Let's do 4, 2, and 3. I don't want to have any repeats here. All right, so this is not going to be drawn to scale very well. If you'd like to borrow a ruler, I've got some up here. Help yourself. It's going to be handy for this problem. But the first coordinate, 0, 0, 0, is pretty simple. That's where your axes meet. So that's this one right here. Now the next one I've kind of drawn in for us. But we're going to use that to try and sketch in everything else. So this is going to be your point 4, 2, and 3. We're going to try and make this the opposite vertex of a box. So I saw one person taking advantage of the rulers. Probably going to be a couple more walking up here. This is going to be another vertex. And then we'll connect these two here. Yeah, Mod, why don't you just pass those out? So that gives me one face of my box. Draw this parallel to this side here. That is your x-axis. These are x, y, and z respectively. I'll connect that one as well. Let's draw another bar. It's going to be the same distance as this, starting out here. So that distance for me is about an inch. So I'll draw something about an inch high right here. And then again, keeping things parallel, we'll fill in this side. And last but not least, this side. There's our box. Our goal now is to try and label the rest of these sides. I'll give you another minute to try and catch up on copying down that box. So a brief pause. If you're done filling in that box, you can try and fill in this one as well. Maybe we'll do another practice one. But let's see about the coordinates here. We're going to start out at this coordinate. Now if I move down to the xy plane, which coordinate am I changing? Am I changing the x, y, or z? The z coordinate. So if I come down here, Now I'm going to be at the same x-coordinate, the same y-coordinate, but the z-coordinate is going to be 0. So that's going to be my new coordinate there. Let's move this direction. If I move over to the x-axis from here, now which coordinate am I changing? The y-coordinate. And on the x-axis, what's the value of the y-coordinate? Anyone? 0. So the coordinates here are going to be 4, 0, and 0. Do you want to try filling in the rest of these? There's 3 more. All right. Is that a good little challenge? You can move north, go up here and get this one, or you can come from this point over here to get this point. So there's 3 more points to fill in. It's hopefully a friendly problem for you on an exam. Is if I gave you a box like this, ask you to fill in the rest of the coordinates. What about that one? Okay. All right. Yalla. Oh, I understand. You probably didn't have any coffee this morning. All right. Give you another 30 seconds or a minute, and we'll look at these together. Yeah, you want to be careful where you write these things so that you don't crowd everything inside the rectangular solid here. Yeah. All right, so probably a couple ways to think of what's happening at this point. You could start out here at 4, 0, 0 and go up. Now, if you go up, which coordinate are we changing? Z coordinate. Z. All right, somebody spent some time overseas there. 4, 0, and then 3. Likewise, you could think of it as coming from here, and you're changing the y coordinate. When you get over to the xz plane, the y coordinate is 0. Let's go from here back to here. Which coordinate am I changing this time? The x coordinate. So if I go back to the z-axis, then this is going to be 0 in the x direction, 0 in the y direction, and 3 in the z direction. From here, I can move out to this point. Moving along this direction is changing the y coordinate. So my new y coordinate is going to match this one as well. So it's going to be 0, 2, and 3. And I think there's one last one that we have to get, which is this one down here. Which way do you want to do it? You want to move from here or move from here? Either way, you can come up with that. Let's go down from here. If I come down from here, I'm changing the z coordinate. So that's going to become 0, 0, 2, and then the z coordinate is now 0. So 0, 2, 0. Nice. These points, let me underline them. This one here, this one here, this one here, are all the points that are strictly on the individual axes. So, how are we looking with that first one? Okay. Now, there's a couple problems in the book that give you, boxes like this to design that have points other than 0, 0, 0. That's starting to get a little complicated, so I'm going to keep it friendly for you. I promise that I will give you 0, 0, 0 as one of the coordinates of your box, just to try and keep these problems a little bit user-friendly. All right. Any other comment on that one? Yes, sir.
So are we looking at it from like a
Uh, if we regard that as east, north, then I'd say we're looking at it from the southeast or towards the northwest. Um, yeah, I guess I look at that as being east. So I'm putting myself here and looking kind of northwest. So, and of course that really only applies to this plane here. So yeah, let's move on from that. I don't want to get everyone all messed up here. Now, just like we did with our other points, we're going to figure out how to start out with a couple points and come up with a vector. So let's take a quick look at problem number 30. We've got points at P equals -3, 2, 0, and Q is 6, 5, and -1. Did we? All right, well, we'll do it again because I want it on the video. 6, 5, and -1. I don't think I posted a video for this last week. So we want the vector, where is it, PQ? Yeah, initial point of P and a terminal point of Q. So I'll write it like this, PQ. And I'll use angled brackets to reflect the fact that this is actually a vector. To find that vector, you're going to subtract the coordinates in pairs. So x, y, and z, x, y, and z. 6 minus -3, 5 minus 2, and -1 minus 0. 9, 3, and -1. Now that's one way to express this vector. Another way to express this vector depends on so-called unit vectors. We've had unit vectors before in this class. Now that we're in 3 dimensions, we're going to extend those. I is going to be this vector, 1, 0, 0. J is going to be this vector, 0, 1, 0. And K, quite naturally, 0, 0, 1. These are unit vectors because if you calculated their length, they're 1 unit long. With these unit vectors, I can express this as 9 times I plus 3 times j minus k. So this is an equivalent way to write the vector from problem number 30. Let's work on finding the length of a vector. So this is the length of vector v. Now v is going to be this vector, a, b, and c. Or you could also write it as ai plus b times j plus c times k. Either way. But the length of that vector has a formula that's similar to what we dealt with in the two-dimensional case. It's going to be the square root of the sum of the squares. So the square root of a squared plus b squared plus c squared is going to be the length of that vector. Just adding on in one dimension from what we dealt with in the two-dimensional case. An application of that would be problem number 38. V is 6i plus 2j minus 2k. Now, I use this angled bracket notation just because I can't really write in bold like the book can. So, I mean, the book will write this in bold. I'm not so good at that. So I can also write this as 6, 2, -2. And I use this angled bracket to reflect the fact that it's a vector, meaning you start out at the origin and you draw a line pointing to that point. So be starting out at the origin and draw a line that points at that particular terminal point right here. That's what your vector represents. It's not just the coordinate sitting by itself up in 3 space someplace. It's actually a line to that point. But let's find the length here. So the length of vector v is going to be the square root of 6 squared plus 2 squared plus negative 2 squared. 36 plus 4 again. Square root of 44. Now, I'm happy with it like this. If you check your answer in the back of the book, sometimes you'll see a little bit something different. What they're going to do is they're going to factor out the largest perfect square that they can, and then they'll write this as 2 square roots of 11. I don't care. You know, if you write it like this, occasionally maybe you'll pick up an extra credit point. But you know, I wouldn't worry about that. My goal here is to figure out if you know how to find the length of a vector. So that's it. Looking good on 38 so far. Let's see about problem number 40. So they asked us to find 40. Yes. Now I got to give you a couple vectors in problem number 40. I'm going to give them to you in, I'll use the same form that the book does. So v is 3i minus 5j plus 2k. Likewise, w is defined for us negative 2i plus 3j minus 2k. And what's problem 40 ask us? This is the two vectors that were given, but they asked us to put these together in kind of a unique way. They asked us to calculate 3 times v minus 2 times w. So let's write it out. And in fact, maybe at this point it would be convenient to, well, let's see. I don't know. Yeah, I will go to the angled bracket notation. So if I write this with those angled brackets, that would be 3, negative 5, and then 3, negative 5, and 2. And this would be negative 2, 3, and negative 2. So 3 times v would be 9, minus 15, and 6. From that, I want to subtract 2 times w. What's 2 times w going to look like? Good. Negative 4, 6, and negative 4. So here's your 3v, here's your 2w. In terms of subtracting these, you're going to subtract them pairwise. So it's going to be 9 minus negative 4 is what? 13. Good. So 9 minus negative 4, that gives me my 13, because the double negative becomes a positive. Likewise, subtracting them pairwise here, negative 15 minus 6, good, negative 21, negative 21, and last but not least, 6 minus negative 4. Good thing we're working in 3 spaces, 3 dimensions, otherwise I'd run out of colors here. All right, the last one would be, what, 10. So nothing really too onerous here, I hope. Just combining those, a little linear combination of vectors v and w. Now what I want to get to is a problem like number 42. So another one that deals with the length of these vectors. Are you okay with what we did in problem 40? It's just, I mean, hopefully it's kind of what you would do naturally. If you didn't see me lecture about this, you'd say, all right, well, let's just take the 3 and multiply each of these, and then multiply this by 2, subtract them pairwise. Hopefully that's kind of a intuitive operation there for you. Let's take a look at problem number 42. I want the length of v plus w. Now v and w are the same as they were in problem number 40. So let's put that back up here. Do you think that I could do this as the length of v plus the length of w? No. Typically that's not going to work. So it's not equal to. This is another version of the triangle inequality, but generally speaking, these two things will not be the same. So what do I have to do first? I have to add v plus w. So what would v plus w equal? Good. 1, -2, and 0. See if you can't calculate the length of this vector using the formula that I gave you around problem number 38. While you do that, maybe I'll calculate the length of v and the length of w. The length of v would be square root of 3 squared plus -5 squared. Okay. What'd you get for the length of this vector? Square root of 5. Good. So square root of 1 squared plus -2 squared plus 0 squared, which we really don't need to write, is square root of 5. Square root of 5 is certainly less than what you would get if you added up the length of these individually, which would be square root of 38 plus square root of 17. So, yeah, a much different beast in working with that one. Oh, is it problem 44? Oh, good on me. I anticipated the book. Yay. So, one less to do there. Thank you. Unit vectors in 3 dimensions work the same way as they did with 2 dimensions. Define a unit vector, call it u, in the same direction as v is given by, does anyone remember? U equals v divided by the length of v. Basically, you're going to scale it.
Jeff, what does it mean in the same direction? Unit vector and u in the same direction as v.
So suppose that I have something here, a vector like this. It points to here. Now, I don't know how long it is, but you can use the Pythagorean Theorem. It'd be 1.5 squared plus, call it 1 squared. Take the square root of that, and that'd be the length of this. A unit vector says, you know what? Let's scale this so that the length of it is 1. So it's still going to point in the same direction at some angle theta, but it's not going to be as long. It's going to stop right here, so that if you calculate the length, that it would be exactly 1 unit long. So that's what a unit vector is doing. And we can make these things in any dimension. It doesn't have to be just 2 dimensions or 3 dimensions, but any dimension. The formula is still the same. You're just going to scale vector v like this. You can take 1 over the length of vector v times v. And that's going to be your unit vector. So let's see if we can't do that for problem number 48. 48 actually works out pretty nice. Vector v is negative 6i plus 12j minus plus 4k. I'm going to write it like this: negative 6, 12, and 4. The first thing I'm going to need is to calculate the length of vector v. So negative 6 squared plus 12 squared plus 4 squared I need a freeze button for this thing. When I'm recording, I don't have a freeze button. So 36 plus 144 plus 16 is the square root of 196. And isn't that special? Works out to be 14. Yay! But that's not our unit vector yet, right? The unit vector is going to be 1 over v, so 1 over 14 times negative 6, 12, and 4. You could, if you wanted to, distribute that and write it as negative 6 over 14, 12 over 14, and 4 over 14. I probably would appreciate it that if you did write it like this, that you write it in lowest terms, so negative 3/7, 6/7, and 2/7. So there's your unit vector. It points in the same direction, it's just a little shorter. In fact, how long is this? Yeah, 1 unit long. How could you show that if I wanted to check it? Yeah, just use your length formula, right? So if I wanted to check it, the length of u would be the square root of 3/7 squared plus 6/7 squared plus 2/7 squared. And let's see what we get here. It's going to be the square root of 9 over 49 plus 36 over 49 plus 4 over 49. And wait, let me get out my calculator while I calculate the square root of 49 over 49. 1. So it checks. Yes?
Sorry, I might have missed it. When you asked how long is this vector, we said a unit of 1. How do you know what?
That's what we created.
That's what
You're creating a unit vector, so by definition you're creating something that's 1 unit long. So yeah, that's the definition there. Is that high enough? Okay. Anything else on 48? Now I know it was a long week ago, but you may remember us working with a formula back in section 5.6 that allowed us to calculate the angle between two vectors. That formula works here just as well as it worked in section 5.5, even though here we're working with vectors in 3 dimensions. So let's work on that. Last little thing that I need to cover here is to find the angle between, actually I think there's 2 things here. But let's finish up with finding the angle between 2 vectors. So as a reminder, the cosine of theta, the cosine of the angle between 2 vectors is going to be the dot product of those 2 vectors. So v dot w divided by the length of v times the length of w. Let's see if we can't figure that out for a couple problems. I'll start with problem 52 because it has a special result. V is I plus j. W is negative I plus j minus k. Well, let's write it like this. 1, 1, 0, and negative 1, 1, negative 1. The dot product here is just the same as it was in the last section. It's just we've got one more thing to take care of. So let's do the numerator first. Let's do v dot w. And to do v dot w, we're going to multiply those 2 together and then add in the product of the y coordinates and then add in the product of the z coordinates. So let's see what that looks like. This is going to be your dot product. 1 times negative 1 plus 1 times 1 plus 0 times negative 1. What do I get for the dot product here? 0. Does it matter what the lengths of each of these vectors are? No, because you've got the cosine of theta is 0 divided by the length of v times the length of w. Whatever these are, they're not 0. 0 divided by this is still going to be 0. So the question is, what angle has a cosine of 0? 90. So theta would be pi over 2, which is the inverse cosine of 0. It's an important result that I mentioned last week. I'll mention it again. If v dot w equals 0, then vectors v and w are perpendicular. Perpendicular, yeah. A little bit too long of a word, which is why mathematicians also use a different word. Do everyone remember it? Orthogonal. Yeah, well done. All right, so none shorter. But it's an important result. It's an easy way to check if 2 vectors are perpendicular. If their dot product is 0, that's it. They're perpendicular. So keep this one in mind. That could be some easy points. Prove that 2 vectors are perpendicular. Well, their dot product is 0, they're perpendicular. That was kind of a nice special case here. Let's try a different one. Let's try problem number 54. V is 2, 2, negative 1. W is, let's see, it's 1, 2, 3. I'm going to start out by calculating the length of V and the length of W separately. And first, square root of 2 squared plus 2 squared plus negative 1 squared. That works out pretty nice because that's just going to be a 3. I don't think the other one's going to work out quite as nice. At least I don't think it's going to be something even. 1 squared plus 2 squared plus 3 squared. Square root of 14. And of course, that doesn't simplify. Why don't you see if you can come up with the dot product, then put all those things together. Cosine of theta is the dot product divided by the length of v, which is 3 times the square root of 14. Finish it up by seeing if you can't figure out what theta is. Does anyone need a bar calculator? We're doing those. Put your calculator in degrees for this one. It'll be a little bit easier to understand the angle as opposed to looking at the angle of radius. Okay, so v dot w is going to be 2 times 1 plus 2 times 2 plus negative 1 times 3, 2, 6, 3 for a total there. So putting that into our formula, v dot w is going to be 3. Before you go plugging this all into your calculator, do yourself a favor. Cancel out that common 3. Cosine of theta is going to equal 1 over the square root of 14. There's no bonus points for rationalizing it. You could write it as root 14 over root 14. That's fine. But basically, you want the inverse cosine of 1 divided by the square root of 14. And let's put our calculator in radians, or excuse me, degrees. And boom. About 75.5 degrees. And on an exam, I would tell you where I want this rounded. So about 74.5. I'll call it 499. All right, 86. Fine. Somebody's really dramatic. Yeah, he's got it memorized. He's a savant. All right. How are we looking on problem 54? So kind of a nice review problem of sorts from stuff we did last week in section 5.5. Are we good with that one, or do you need another one? Yes, sir. Hans? Yeah, but you still have to enter it into your calculator and take the inverse cosine, so it wouldn't change it. Yeah. Your calculator doesn't appreciate the beauty of a rationalized expression, so it's kind of lost on it. It's like giving a really good cup of coffee to me. The beauty would be lost. Actually, good cup of coffee sounds to me like an oxymoron, you know? Kind of like jumbo shrimp and military intelligence and that kind of thing. All right. There is one last little topic in this section, and that is to find the direction cosines. So a different way to specify a point is to specify its length and the direction it makes with the positive x, y, and z axis. So here's a general point, A, B, and C. It has these coordinates along the x-axis. So A0 and 0 along the y-axis, 0, B, 0, etc. To find this angle, really what you're going to do is find the angle between this vector and this vector. So we're going to treat this as A0, 0 and find the angle between these two vectors. Okay, so let's see how that works. And we're going to work that with a problem that we've kind of already done a little bit for, which is problem number 60. In problem 60, we've got vector v, and I'll zoom out a little bit here. Go. Is negative 6, 12, and 4. Negative 6, 12, and 4. Now the nice thing about this is we've already calculated the length of this vector. The length of that vector is, what was it, 14, right? Yeah. That was a previous problem. If we want to find the angle that this makes with the positive x-axis, that is your direction cosine, then it's enough to look at the dot product of this with the vector 0, 1, 0. Let me make this even a little bit shorter for you. To find the angle that this makes with the positive x-axis, you're just going to take this and divide it by the length of v. So negative 6 divided by the length of v. To find the next angle, we'll call that beta, cosine beta, is going to be 12 divided by the length of v. And cosine gamma is going to be, well, any predictions? All right, way to go out on a limb on that one. I appreciate the bravery there. 4 divided by the length of v. So how's that work out? Cosine of alpha is going to be negative 6 over 14. So alpha is going to be the inverse cosine of negative 6 over 14. And again, you can put this into your calculator like this. Your calculator is not going to really thank you and put you on its Christmas card list if you reduce that and put it in lowest terms. So just finish it up here. Inverse cosine of negative 6 divided by 14. So 115 degrees. Let's round this to the nearest hundredth. So that'd be alpha is approximately 115.38. Cosine beta is 12 over 14. Here's a cute little trick. I've already done one of these, right? So to do another one, I'll do this last. Let me just do this one, then I'll show you that cute little trick in just a second. Cosine inverse of 12 divided by 14. This time I get 31.00. Now if I'm asking you to round this to the nearest hundredth, then there should be something in the hundredths place. Beta is cosine inverse of 12 over 14. 31.00. And last but not least, gamma is going to be the cosine inverse of 4 over 14. We've already done a lot of these. So here's the little trick I was going to show you just a minute ago. If you hit the second button and then the enter key, it'll pull up your previous calculation. And then you can just go back and make some changes. I'll delete that and type in a 4. There you go. Not a big savings, but convenient. So gamma is about 73 point, ooh, good question. If I'm rounding this to the nearest hundredth, what would that be? 40. Good. There has to be something in that hundredths place if you're rounding to the nearest hundredth. Overall, you can write vector v as negative 6, 12, and 4. But if you're looking to know what angle that each of these things makes with the respective axes, you could also write this as 14 times the cosine of 115.38, then the cosine of 31.00, and finally the cosine of 73.40. On an exam, if I gave you a problem like this, I'd tell you that I want your vector written as the length of v times the cosine of alpha times, or cosine of beta and cosine of gamma. So that's probably how I'd ask to see it written, just like we have it written right here. Yes, sir.
So that's from the origin?
Yes. So to kind of give this a visual perspective, our point here would make an angle of 100 and, let's see, 100 and what was it, 13? 115 degrees with this axis. So it would be here in this quadrant someplace, or this octant, I guess would be more appropriate. So it's past what we have because we're no longer in the positive region of this space. But the other two would be, you know, something we could recognize. Beta was what, 31? So that would be 31 degrees from the x-axis, or from the y-axis, and then 70-some degrees from the z-axis. Okay? And the length was 14. Let me give you some homework. Whew, yeah, I don't know. Finally the good stuff. Thank you, Shane. 21, 27 through 43, 47 through 61, and 65. Cool. Yes, sir.
And that last step, 14 times that,
Yeah, this is the length here. 14. It's not a sum. It's just it's a vector. Yes.
where did that come from? How do we know to do that?
I would show you that this is the form that I want it written in. But if you were to kind of unravel this and say, well, gee, that just doesn't look right, then to unravel this, to kind of show yourself that this is actually what I claim it is, let's realize where I got alpha from. Alpha is the inverse cosine of negative 6 over 14. So if I take the cosine of alpha, I should get negative 6 over 14. So rewriting this, that'd be 14 times, well, the cosine of that is negative 6 over 14. The cosine of this one is 12 over 14. And the cosine of this one is 4 over 14. If I distributed that, then I get what I started out with. So it's a different way to write it, but it's allowing you to get your hands on those angles. So if you needed to figure out, well, gee, how far away am I? How much pitch? How much roll? How much yaw? How have I turned? Then that's how you get your hands on those angles. Okay? So good question.